and I have like half an hour probably, or more than that.
Hour would be amazing. That's fine with
Half an hour with the questions.
you. Half an hour and 10, let's say 10 minutes for questions.
That would be wonderful. Okay.
Okay. Great. So I think, okay, let's wait for a couple of more minutes for people. I think it's Chinese New Year, so many people are not around.
Sure, I know.
Oh, I forgot to record it. Okay. A special thank you to Hamid who accepted our invitation. We cannot wait to hear about your amazing research. So for a bit of background, Hamid is a PhD candidate in University of Alberta in Canada, and he's working with Eric Krosolowski. I hope I'm pronouncing it correct. And he's mainly involved in PHANGS collaboration. I tried to remember what it stands for. It's physics of high angular resolution galaxies in nearby galaxies.
Yeah, that's right. Yeah.
Yes. So, okay, let's start. Thank you, Hamid, for
Thank you so much.
joining us.
Thank you so much, and thank you for giving me this opportunity to talk about the James Webb and some other things that I'm really interested. That's right. I'm a PhD candidate. I wrote a PhD student, but I'm a PhD candidate after a couple of months now, and I'm studying the mostly ISM in galaxies. So I had a paper a couple of years ago, not a couple of years ago, 2 years ago, I guess, but it was mostly about the early observation of James Webb Space Telescope of 4 galaxies. And this is going to be my third paper of my PhD, which is not submitted yet, but the title is The Hidden Life of Stars, Embedded Beginnings to AGB Endings with the Mid-Infrared Peaks in the PHANGS-JWST sample. So I'm in PHANGS. PHANGS stands for Physics in High Angular Resolution in Nearby Galaxies, and we mainly study ISM. So that's all. I just want to start the presentation and today with one single image of a galaxy called NGC 1566 at a distance of about 15 megaparsec. So this image was taken by Robert Kennicott 2007, more than 10 years ago, with a Spitzer. And the Spitzer at 24 micrometer studies dust. And this is specifically coming from the heating of dust grains, stochastically heating of dust grains by the young stars that you have in your galaxies, which are re-emitting at the near or mid-infrared from 5 to 24 micrometer. So these are dust-emitting particles that you have in galaxies. And this is really important for us because it's helping us to answer a couple of really important questions which are necessary to understand the galaxy formation and evolution. So we need to map dust emission in galaxy, first of all, because of understanding star formation rates, understanding the early stage of star formation process, which is the embedded in dust. At the earliest stage of a star formation, we have lots of dust and stars are not really formed yet. And James Webb can actually help us understand these stages. You want to also understand the dust properties. What is the size? What is the charge of dust grains? And ultimately, you want to also look at the correction factor for dust attenuation. When you observe galaxies with the optical bands, there's always an attenuation factor that's coming. And with these maps, you can actually correct the dust optical maps. But this is not enough, right? The resolution of this picture is about, this image is like 7 arcsecond, which is like half a kiloparsec. So you can really resolve the structure in these galaxies. But later on, a couple of years before, people in PHANGS came up with this idea of observing galaxies, same galaxies with James Webb. And this is the same picture with the James Webb of the same galaxy. So this is NGC 1566, PI is Janusly, and the red one is actually maybe 21 micrometer, almost the same as 24 micrometer-ish MIPS. And there are two other colors here, orange one and the cyan one. So these are the pH. heavy molecules, right? You heard about them before probably. PAH stands for the polycyclic aromatic hydrocarbons, and these are the emission mechanism is different with the medium infrared emission. These are coming from the vibrational rotation of the molecules that you have in galaxies. So you can see the pH, you can see all of these red things in galaxies, but still, this is not enough, because if you want to study clusters of stars, if you want to study stars, you need starlight, and then you need optical emission. And having the same galaxy observed by any optical telescope would be super nice. And that was the reason we also have the Hubble telescope observation of the same galaxy. So this is the same galaxy. This part is just separated by two a nice telescope here. And this is the James Webb observation. This is the Hubble observation. Hubble is telling you lots of information about the younger stellar clusters, stars, foreground stars, I would say. And also James Webb is telling you a lot about the bubbles, about the stars, dusty stars, and the structure of the dust in galaxies. But if we just zoom in a little bit here in the part of the James Webb observation, we will see lots of fluff, lots of point sources in galaxies, which seems strange. And that's my question. What are these sources? What are these point sources? What are these things here? Are these young clusters? Are these stars? What are these things? Are these background galaxies maybe? So that's the question for today. But before answering that, I want to go a little bit about the star formation in galaxies. So you know that the star formation is starting with the dense, cold molecular gas that you have in galaxies. But after a couple of million years, this molecular gas is just contracting under its gravitational potential and just heating up, which is helping to form the earliest stage of stars. So these little blue and yellow stars are the earliest stage of stars that are being formed. You're still in the dust and you won't see them because the AV of this region is like 10, or the EBV of higher than 5 magnitude. But after a couple of million years, that's a phase that you can see with the optical observation, right? This is the phase we call H2 vision, or the ionized hydrogen gas. We know this is well defined, that it has a temperature of 10 to the power 4 Kelvin, and the feedback mechanism is here because it's just wiping down all of this material, wiping away all of these materials, and just all of these dark grains are going on the edges. And you will see all of these young O and B stars with the mass of more than 19 solar mass. This is the phase which is also associated with the recombination lines, like the H alpha. And then after a couple of million years here, the molecular gas is gone because of the feedback, because of the radiation from the stars, and it will end up with the evolved clusters or single stars. But observationally speaking, you can trace this phase with the molecular gas, like the carbon monoxide transition of 2 to 1, and the other phases, this one, which is called the embedded phases, earliest stage of star formation, 1 or 2 million years at the beginning, which are like bright at the mid-infrared emission and the pH bands. After that, you will have the H2 vision phase, which is bright at the H alpha or any other recombination lines probably, and the pH bands. And finally, you will see all of these evolved cluster or red dots, which are the stars traced by any other BVI optical telescope. I want to emphasize here that the two stage of star formation here, one of them is well studied before with any other telescope that we have for distant galaxies, exposed vision or the H2 visions, because it has recombination lines. But it seems there is a phase before that there is no H alpha, because the H alpha is still not originated yet. It's still, the medium is extremely dusty that H alpha cannot escape from the medium. So this is the phase that called embedded phases versus a exposed phase. So the question that I have, how we can find the stars, clusters with the medium infrared observation, and what are the properties of those sources? So I want to start with physics and every models that we have in physics to understand distinguishing between all of these different sources that we have. So we have a really good understanding of different kind of sources in galaxies, starting with the young clusters. So this is the spectral energy distribution plot, starting from the NUV of the Hubble to 21 micrometer. Everything that you see here is just model scaled to a distance of like 5 megaparsec for one of our nearest targets. And the black line here is just one single young cluster. with the age of like 1 or 2 million years. And it has several important features. It has a bump at 3.3 micrometer because of the PEH emission, small loss grains at the near infrared. It also has a dip at 10 micrometer, mostly because of these bump at 10 or 11.3. These are again PEH band. This one is mid-infrared bands. These are the PEH band, vibrational rotation of the dust grains. And you will have a really bright 21 micrometer. But if you add lots of dust to that embedded cluster, you will see that the optical part going to be really faint. This difference between the solid one and the dashed one is just the amount of dust, the AV of 0 between and versus AV of 10. And you have some other kind of stars here. You have the red supergiants, OAGBs, and CHGBs. I won't go really into the details of different models here, but different stars are here are just modeled with the Parsec tracks. And you can see that most interesting theory is that CAGB stars or carbon-rich AGB stars, the tracks that we have, they have a really positive slope at the NavCam, and they have a bright 7.7 and 11.3 pH band as well. And all of these different stars are detectable at 10 micrometer. This is the detection limit of about 5 microJohnsky for one of our nearest targets. But the red supergiants are not detectable at the 21 micrometer. And some other stars as well. So at 21 micrometer, you will end up with clusters. At 10 micrometer, you will end up with most of the clusters at most of the stars that you have. So these are different models that I have for different sources. Thanks to all of this information, I came up with the one classification scheme to just classify different sources here. So observation, PHANGS studies main sequence star forming galaxies, and it means that all of these galaxies that we are studying, they have a stellar mass of about 10 to the power of 10 solar mass, and anything is a star formation rate higher than LMC, higher than 0.1 solar mass per year. And we started with 19 galaxies, observing with them ALMA, and then HST, and then MUSE and JWST. And we are extending samples so far. We have another observation cycle with the James Webb to observe more 55 galaxies. I also have another paper studying all of these galaxies with the FUV bands, with the AstroSat. AstroSat is a wonderful telescope, which is kind of similar to the Galaxy, but it has a better resolution. So these are the sample, and these are the galaxies, actually. These are the 18 galaxies, 19 galaxies in our cycle. I'm showing just 18 galaxies here. The red color is 21 micrometer, 10 is green, and 2 stellar emission is just blue, bright in these galaxies. And all of these boxes that you can see, white boxes, are the footprints from the HCH alpha. We have both MUSE, IFU data that is just MUSE from 3,000 angstrom to 9,000 angstrom. We also have the HCH alpha resolved observation, because HCH alpha has like an angular resolution of about 0.1. Any H alpha that is what's taken on the ground, it cannot have a resolution of higher than 0.8 oxygen. So these are our sample. And the question that I want to start asking is that what are these peaks? If we're looking at the bright sources in galaxies at 10 and 21 micrometer emission, what are these sources and how they look like? So this is 3 different kind of source that visually you can see in the galaxies. This is 21 micrometer peaks. These are the 10 micrometer peaks. So most of the sources in galaxies, you can actually classify them into 3 kind of sources. First one is the circular one, round objects. Second one are the elongated objects. And the third one are the kind of irregular objects, right? And this is the beam, I won't say beam here. This is the aperture of the 21 micrometer resolution. This is like 0.67. Translate that's 20 parsec for this galaxy. But thanks to the 10 micrometer filter, this has the better resolution. This has like the resolution of about 0.3 oxygen, better than 2 factor here. So you can really resolve the structures here, right? So this is again telling us this elongated structure was a background galaxy, actually. And these 2 these one irregular structure with just 2 sources at 10 micrometer. So the question that you can ask is, how do a young stellar cluster appear in your galaxies? This is one extremely good example of a young cluster, embedded clusters, because it has a bright 21 molecular emission, it has a bright pH emission, this is the center of the source, and there is no star. There is no star detected in the center. There is no blue star emission. There are lots of stars are here, but nothing in the center. This is mostly because of insanely amounts of reddening and dust that you have AV of higher than 10, that you cannot see stars. And another nice story here that all of these contours that you have from CO monoxide, carbon monoxide, is just tracing 21 molecular emission as well. If you're just looking at the Hubble bands, NUV, all of these LUV to the V band and H alpha, you won't see any source here, you won't see any star here. But using the NearCam bands, you would see this cluster, young stellar cluster here. So for this paper, we are convolving everything that we have from Hubble's band to James Webb band to the 21 molecular emission, as well as for the 10 molecular catalog, we are convolving every information to 10 molecular emission. So there is another thing here. What about the dusty stars? How they look like in your galaxies? This is a James Webb view of the one single field in the nearest star yet, and this is the V band of the Hubble. You will see lots of single isolated sources that are not real clusters. Those are single stars, but these are like dusty stars. This could be red supergiants, AGB stars. So they are bright at 21 micrometer and not detected at any of the V bands, any V bands here. And we want to understand what are these dusty stars. If they are RSGs, if they are like the OAGBs or CAGBs. Another question that you can ask of, where are these peaks? Where are these bright point sources? So this is the most simple plot that you can come up with and tell what is the distribution of the flux in different environments in galaxies. So the red one is the 21 micrometer point sources, and 10 is the 10 micrometer point sources, or hereafter peaks, I would say. So you would say that the most bright sources are in the center, as you might expect, because of lots of nuclear sources that you have, lots of youngest massive clusters that you have in the center. And then most of 21 micrometer or 10 micrometer bright sources are actually in S-spiral arms as well as barons. You might expect spiral arms because you have lots of star formation in the spiral arms, and then you expect lots of dust as well. But barons are also interesting because of the shear and lots of other studies that have been showing in the barons of a couple of galaxies, insanely amounts of dust, and the H alpha is still in the barons and active forming. They are forming active sites of star formation rate. What are these peaks? So if you want to answer the nature of, if you want to understand the nature of these peaks, you can use Seagal, all of those CD plots that I show you. You can use Seagal to understand the stellar clusters and the parsec to understand the properties of stars. I won't go into details of what is my Seagal code, what is the input parameter. Like we have included every single different star formation history, different dust contents, different nebular parameter, as well as parsec to evolve stars. But here I just wanna compare the observation and came up with just one single parameter, physical parameter, that can describe the variation in the data. So this is the really simple plot. This is the 3.3 divided by 3.6, 3.3 divided by 3. This is the same plot here. So these dots here are the observation, 21 micrometer sources. And this is telling me that the most of 21 micrometer sources are here. And this is the same plot here as well. So I'm just plotting here the variation of the age for the NearCam bands here. So as you might expect, if you have brighter 2.3 relative to its continuum 3 or 2.6, you will have younger ages. Here you will have younger ages, and after a couple of million years, pH is gone. So for a cluster of like 10 million years, you won't get any pH. So the ratio of the pH relative to its continuum is just 1, right? So most of the old clusters are here. But on the other hand, the variation, vertical variation, can be explained by the QPH, or the relative amount of the pH to the total dust mass. And you can see that most of my sources, they have the QPH of about 1 or 2%, right? And that's interesting because QPH is fraction of the pH in the star forming region. And this is telling me the QPH in these star forming regions are really low. And that has a reason, right? Most of them are being destroyed. Most of these QPH particles are being destroyed in the H2 vision, and we know that previously from a Spitzer observation that in H2 visions, QPHs are extremely low, and that's the reason that we see the QPHs about 1 here. So NavCam help us to understand the QPH, age, and the slope of the mean. I don't want to go into details of the terrain parameters here. But on the other hand, MIRI observation is the relative. I am showing here 11.3 to 10, 7.7 by 10, and these lines, these gray lines, are the classification that I had previously from my previous paper based on the visual inspection. But actually, maybe bands wouldn't help you much about the age of the cluster, and that's interesting. Most of that is helping you with little bit information of the QPH. That's all. That's the most important valuable information that you can get out of the maybe bands for the your observation of the young clusters. On the other hand, for stars, I have lots of models. I'll show you a CD, right? So this is the NavCam plot, exactly same observation on the background, and this is the MIRI one. So I want to start with this one. So this is from my models. This is telling me most of the CAGB stars, most of those AGB stars with the age of 700 million years and the mass of below 504 solar mass are about here. And the rest of the stars, like the RSGs and the OEGB stars, are here, right? But you know that the modeling of the rest of the stars is really complicated. Like the BE stars, the stars with the rotating circular stellar disk, and the Wolf-Rayet stars, and the Planetary Nebula. It's complicated to model all of these different things. And we just use the SEG LMC observations. We know what they look like in the SEG in the LMC. We translate them to the filter of the James Webb, and they look like this here. So most of the stars are here in the maybe bands that's just specifically shown here. So finally, thanks to all of these different filters, thanks to all of these different models, we can classify sources, right? We can classify sources into two kind of sources for the clusters: exposed and embedded. Exposed is with H alpha, embedded is without H alpha, and they are mostly here. This is color diagram. Y is 2 micrometer minus 7.7, X is 2 micrometer minus 3.6. Most of the clusters are here. Any cluster with like mass with the age of like below 4 or 3 million years are here, and the stars are here. Most of the stars are here. These contours are separating two different kind of stars, two different kind of sources: stars, clusters. So this red one are the CAGB stars, gray one are the BE stars, and the RSGs and OEGBs are here. This is for the FANGS sample. This is for the nearest sample, for the nearest targets that we can reliably just resolve single stars and just classify them. But in the case, if you want to compare these results with what we have from LMC and all of those spectroscopically confirmed sources, you can take a look at the SEG sources. So SEG is telling me actually most of H2 visions are here, right? This is in a good agreement with my results. And SEG is also telling me most of RSGs are here. These are the RSGs, these dots, and these contours, you can see them here. This is from my models, these green contours. And ultimately, SEG is also telling me that most of the CAGBs are here, this black one, the red one are here, the CAGBs. Also, SEG is telling me there are kind of other stars, like C post-AGBs. They're extremely dusty, carbon-rich AGB stars where the ratio of the carbon to oxygen is higher than 5. This is telling me some of them are here. So I wasn't able really to classify a couple of these CPAGBs because of the parsec tracks, because parsec tracks doesn't really include CPAGBs. It just goes until the CAGBs, not CPAGBs. So that's one important point here to remember. And then again, going to back that flux distribution plot. What are the bright sources in the galaxies? Exposed sources. Any young cluster with H alpha are the brightest at 10 and 21 micrometer. What about the rest? They are kind of similar to each other, I would say. Sometimes CAGBs are brighter, sometimes our RSGs are brighter, but mostly embedded sources are as in terms of flux, they are not really distinguishable. You can see that this blue one or the exposed one brighter, and the rest of them are not really distinguishable here. So these are the peaks and that I have in galaxies. So this is my last plot, and I'm gonna take a couple of minutes here. So this is the most important plot that we had in my previous paper as well, but this is updated with more sophisticated models of the star formation history, different star formation history. So on the Y, this is the H alpha luminosity of all of these peaks, all of these sources of 21 micrometer sources, versus the 21 micrometer emission. H alpha, 21 micrometer. And this is corrected for loss attenuation, right? We have all of this information from Muse, EBV, everything that we have, all the documents from Muse. And this is telling us that H alpha and 21 micrometer are actually tracing each other for more than 4 orders of magnitudes. This is really nice. This is telling us that most of 21 micrometer sources, they have counterparts of H alpha. So you can easily say they are young. Any 21 micrometer sources are below 2 or 3 million years. So we also use the Seagull to feed the SED with all of his information, all of his different CD parameters that we have. And we use the CB19 models instead of the BCO3 regular models. Because in my previous paper, I used BCO3, but there are some minor issues in BCO3. It doesn't have the binary interactions. It doesn't have the improvement treatment for the helium-2 ionization factor, which are sometimes important in these observations. But I used CB19, and we realized that ages of 21 micrometer sources are always below 5. Most of them below 3 or 2 million years. These are the sources. So you can see the color code is age, and this is the age of the sources. And I also scale them based on the stellar mass. So brightest one, most luminous one, and this is decreasing. So they have a stellar mass of about 10 to the power 4, 10 to the power 3 to the 10 to the power 5. And another point about the CB19 is it is just a stochastically sampled as well. So other points here that I want to mention, these all of these black points here. These are the embedded sources. These are faint in H alpha. These are the upper limits of the H alpha that we had, but these are not really detected in the H alpha because of the completeness limit. So these are the upper limits that we have. So you will see most of them are deviating from this relation. They are not really linear here. So these I'm not showing all of the points here. Just randomly sample of the 100 sources here. And this is telling us lots of information about how 10 and 21 micrometer sources are tracing each other in the galaxies and embedded sources here. So just want to end up here with what we learn here new from James Webb compared with Spitzer observation, right? So SED feeding of the sources, 10 and 21 micrometer sources, most of them are extremely young, 1 to 3 million years. And they have a stellar mass of about 1,000 to 10 to the power 5 solar mass. Some of them they could be 10 to the power 6. Some of them could be a little bit higher in the center of the galaxies, in the nuclear sources, in the superstellar clusters, as you might expect. So 25% of the sources are deeply embedded phase and deeply embedded star-forming regions, 10%, 12%, and 21 micrometer. Actually 55% of our sources are the H2 region with bright H alpha. So exposed sources, as I said, is of H2 region. Most of our sources are exposed sources. 27% of them are 10 micrometer, and the rest of sources are just the stars. 12% of them are the CAGBs, 8% of them are the RSGs, and the OGBs stars. So I can just end up here and leave here this wonderful galaxy NGC 5135, which is part of another cycle of our observation, cycle 2, which we are aiming to observe 55 more galaxies compared to 19 galaxies that I observed here and studied here. So we are going to have 55 more nearby galaxies soon. That's all. Thank you.
Thank you, Hamid. Thank you. It was amazing. Very nice work. And I would like to start the question. So I know, as you mentioned, that you have a very good number of observations for your galaxy. I'm just curious about the selection criteria for your observations.
Okay, about the galaxies, right?
Yeah.
So more than 10 years ago, people started with looking any galaxies, any massive galaxy, more with a solar mass of higher than 9.5 solar mass, and a star formation higher than LMC. So a star formation higher than 0.1. So they found like 200 galaxies in the sky, and they just looking at the galaxies below 25 megaparsec, because that was the scale to the Hubble that can just resolve things for like a resolution of below 40 parsec, 30 parsec. And they started with ALMA actually at the beginning. They started observing those 19 galaxies with ALMA, and They had all of these galaxies ALMA with 1 second, 1 arcsecond resolution observation with ALMA, and then they came up with the HST. So HST observed 38 of them, which are below 20 megaparsec, and they can resolve the stellar properties. And then we start observing them with every single telescope on Earth or in space, with the Muse, with James Webb, and then I observe them with the Astrosat. So these are typical scale Andromeda, scale M33 to distance of like 15 megaparsec, and you get the same results. And there is no dwarf here.
Okay. Any other questions, Mike?
Hello, great talk. Thank you for coming. I just had a quick question. So all of your data is photometry. I'm curious if there's any plans to get spectroscopy for the FANGS sample, and then if so, like what are the plans? Like what would you do with it?
That's right. Everything that we have here for JWST is 2 micrometer, 3, 3.3, 3.6, 7, 10, 11, 21. This is all photometry. We never had any spectroscopic data. Most of them, none of our proposals get accepted. It is really challenging to get any data from James Webb, as you know, and writing a proposal and getting some data out of that is extremely hard. But we are writing some proposal every year for getting some near spec or mirror spec of the IFU or spectroscopy of the FANGS, but we never had a chance. So we fingers crossed, cycle 4, we maybe get some spectroscopic observation. It's not our team, but lots of other proposals I will see from other people as well. But still, for FANGS target, not from our team or not from any other team on this on the James Webb, there is no any spectroscopy, a spectroscopic observation, as far as I remember. There are some other targets though, some dwarfs, some other galaxies, nearby galaxies, but no any spectroscopy for these targets available.
Just real quickly, I think on the previous slide you said that there was Muse data. I'm just curious, or maybe I'm
yeah.
I'm just curious, like what happened to the Muse data? Just out of curiosity.
Yeah. We still, by the spectroscopic data, I would mention the infrared spectroscopy, but the Muse is from 3,000 angstrom. It's mostly optical, right? To 8,000. We still have Muse, and we are using them. Actually, most of our results that we had in the first early results was based on the Muse. But the biggest problem with the Muse is its resolution. It is wonderful. It was amazing before James Webb. The Muse resolution is at least higher than 0.8, right? Because of the seeing limited the results on everything that you have. But we use most of the Muse results for the classification, BPT diagram, plant renewable versus H2 vision, and lots of other things. We are using them, but I have not really used them because most of that is because of the resolution. With the 10 micrometer, I can go down to the resolution of like 0.3. Muse is at least 1 arcsecond. So the resolution is important thing here. And I want to study stars, single stars. We can resolve them with Muse.
I have another question, but I'll let someone ask a question first.
Sure.
Hello, great talk, thank you. So I had a question, really quick one, about the seagull results you showed us. You mentioned that you have used BCO3 models or have not used those?
I have used lots of different models here. I started with BCO3, lots of different star formation histories at the beginning. And I've realized that the BCO3 fits. The results are in my first paper as well. You can see them in the archive. I realized that this BCO3 is giving me slightly older ages, which you might not expect. So BCO3 is giving me ages of sometimes, not always, sometimes it's giving me age of like 6, 7, 8 million years, which is not really expected. Because if you just compare the observation with the Hubble, you won't expect any dust emission, any pH after 6 or 5 million years. And then I was like, what is going on there? And in this paper, I'm using the CB19, which is updated version of the BCO3. It has the binary interaction. It has some improvement for the massive stars, as well as the helium-2 ionization factors. So thanks to the CB19, it is giving me some other older ages as well. For most of sources, it's giving me younger ages, which is nice. And the other thing that I have to mention here, when I'm just doing the SED with Seagull, I'm convolving everything to 21 micrometer aperture, right? And this is telling me aperture of about 40 parsec, 50 parsec. So sometimes different clusters are mixing with each other. So having age determined for the mixed young clusters, it is challenging. So yeah, I hope I already answered your question. It was a long answer to a short question.
Thank you so much, Hamid. And I see that we have online participants. I forgot to ask if they have any questions. They are welcome to ask their questions. We have time. Okay, awesome. I think we don't have any more questions from you. Oh, Michael, do you want to ask your question?
No one else has questions.
Yeah, of course.
Hi.
Louis.
Just another quick question. So I don't know much about like the FANGS sample or like how it was selected. I'm just curious if there are any AGNs in the sample or if that's something you excluded.
There are two troublemaking AGN in our sample, which are resulted, well, where is the galaxies? Which are resulted in these spikes, which we hate them. So there are two galaxies, NGC 7496, which has the central AGN, I would assume, and NGC 1365. One of them has a central agent. I think 1365 has a central agent. It has a star formation. The whole galaxy has a star formation of 20 solar mass per year. So it's a huge star formation rate. I guess this one has the AGN. And it has a really bright center. So it ended up with all of these bright spikes at 21 micrometer, which mess up with the data. So I guess one of these two galaxies have central agent.
Okay, yeah. Does that like mess with any of like so it messes with the center, of course, but does it mess with like any of the more outskirts of those galaxies, or is it mostly confined to just the center?
Okay, I masked most of the center because it's really challenging to recover fluxes from these little spikes. So I masked most of the center with the PSF thing, and we don't have any center in my observation. Physically speaking, how's the effect of the AGN on the star formation? There are lots of studies, but in my study, I didn't really look if these galaxies with AGN and the star formation sites has a different properties with other galaxies. I might expect because of this radiation field that you have from AGN, it can end up it can end up with lower amounts of the QPH because just destroying lots of dust grains because of this intense radiation fields. But I never talk about in my paper about the effect of the agent on the galaxy.
Yeah, that would be my expectation too, that it would do the harder ionizing radiation, it would destroy a lot of the dust, but it's hard to say anything with just two targets. So
yeah. Yeah, FANGS sample is not AGN based sample. It was two galaxies that we really would love to study, and I think with the MUs, these are not saturated with the MUs, and they have used the BPT diagram to distinguish between the AGN and H2 visions, but not here.
thank you.
Okay, we have one more question from Patty Umna. And Patty asks, this is probably not a question, I'm sure it's not. Why were 21 micrometer lines more luminous than 10 micrometer? Is there any possibility that carbon type stars, so there is more carbon type dust because of they're more luminous.
Okay. This is really hard question to answer. Okay. First of all, I would go by 21 micrometer brighter for the young clusters. I won't go into the stars yet. This is the cluster. So I guess it has a relation, the dust, it has a relation with the temperature of the dust, the radiation, the minimum interstellar radiation field of the dust, and I assume these are resulting in a brighter flux at 21 micrometer. So I think a combination of the radiation field, minimum interstellar radiation field that we have from the rain model, as well as temperature of the dust, result in a brighter 21 micrometer. But for the stars, this is challenging. This is really more complicated than that. I know stars with having that the first part was correct. Stars with having more C to oxygen ratio or C to O ratio of higher than 2, they are having bright 21 micrometer emission as well. But remember, the 21 micrometer filter has a the resolution compared to 10 micrometer is twice lower. So it also messes up with the sensitivity as well because of the relation between sensitivity and resolution. So 10 micrometer has a better sensitivity to pick up the single sources, but these are blended with the background. But physically speaking, I have to go through all. So let me go one of these models that I have. I don't have it for 21 micrometer. Yeah. So these are the flux ratio of 7.7 relative to 10 for different kind of sources. This is not 21 micrometer, but you can, I guess, accept me for the sources. So this is 7.7 divided by 10. This is 10 micrometer. Everything here that you can see here is just model. 7.7 divided by 10, 11.3 divided by 10. You can see for the really younger AGB stars, like AGBs, this blue one is the OGB, this red one is the models of the CAGBs. So you can see for the more younger AGB stars, and as well as at the same time higher C to O ratio, this is going to be brighter. That's all I have for now, but I don't know exactly what is the exact mechanism that's, if you have just two single CAGB stars, what is the exact mechanism that results in the difference of 21 to 10 micrometer ratio? This is a complicated question for me, but I know it has some relation to the CO2 oxygen, carbon to oxygen ratio. I hope it answers your question. That was a long answer.
Thank you, Hamid. Thank you again for joining us today and sharing your amazing research with us. And thank you, everyone, online participant and people here for joining us, for having our second Astro webinar in Aura.
Thank you so much.
Yeah, thank you. Hope to see you someday
Thank you.
here
Thank you.
in person.